next talk will be the ultimate Acorn Archimedes talk, in which there will be spoken about everything about the Archimedes computer. There's a promise in advance there will be no Eureka jokes in there. Give a warm welcome to Matt Evans.
Thank you. Okay. A little bit of retro computing, first thing in the morning, sort of. Welcome. My name is Matt Evans. Acorn Archimedes was my favorite computer when I was a small hacker, and I'm privileged to be able to talk a little bit about it with you today. Let's start with, what is an Acorn Archimedes? So I'd like an interactive session, I'm afraid. Please indulge me. I'd like a show of hands. Who's heard of the Acorn Archimedes before? Ah, okay. Maybe 50, 60%? Who has used one? Maybe 10%, maybe? Okay, who's programmed? Who's coded on an Archimedes? Maybe half. Two. Wait, two. Three people. Great, okay. Three. Okay, so a small percentage. I don't see these machines as being as famous as, say, the Apple Macintosh or the IBM PC. And certainly outside of Europe, they were not that common. So this is kind of interesting, just how many people here have seen this. So it was the first ARM-based computer. This is an astonishingly 1980s, I think one of them is a drawing, actually. But they're not just the first ARM-based machine, but the machine that the ARM was originally designed to drive. Is that a comment for me? Mike? No? Okay. I'm being heckled already. It's only slide 2. We'll see how this goes. So it's a 2-box computer. It looks a bit like a Mega ST to me. It's a main unit with the processor and disks and expansion cards and so on. Now this is an A3000. This is mine, in fact, and I didn't bother to clean it before taking the photo. And now it's on this huge screen. That was a really bad idea. You can see all the disgusting muck in the keyboard. It has a bit of ink on it. I don't know why, but this machine's 30 years old, and this was luckily my machine, as I said, as a small hacker. And this is why I'm doing the talk today. This had a big influence on me. I'd like to say as a person, but more as an engineer in terms of my programming experience when I was learning to program and so on. So I live and work in Cambridge in the UK, where this machine was designed. And through the funny sort of turn of events, I ended up there and actually work in the building next to the building where this was designed. And a bunch of the people that were on that original team that designed this system are still around and relatively contactable. And I thought this was a good opportunity to get on the phone and call them up or go for a beer with a couple of them and ask them, well, why are things the way they are? There's all sorts of weird quirks to this machine. I was always wondering this for 20 years. Can you please tell me, why did you do it this way? And they're a really good bunch of people. So I talked to Steve Ferber, who led the hardware design, Sophie Wilson, who was the same for software, Tudor Brown, who did the video system, Mike Muller, the I/O system, John Biggs and Jamie Urquhart, who did the silicon design. I've spoiled one of the surprises here. There's been some silicon design that's gone on in building this at Acorn. And they were all wonderful people. They gave me their time and told me a bunch of anecdotes that I will pass on to you. So I'm going to talk about the classic Arc. There's a bunch of different machines that Acorn built into the 1990s, but the ones I'm talking about started in 1987. There are 2 models, effectively a low end and a high end. One had an option for a hard disk, 20 megabytes, 2,300 pounds, oh, geez. Up to 4 megabytes of RAM. They all share the same basic architecture. They're all basically the same. So the A3000 that I just showed you came out in 1989. That was the machine that I had. That was, again, the same. It had, the memory controller was slightly updated. It was slightly faster. They all had an ARM2. This was the released version of the ARM processor designed for this machine at 8 megahertz. And then finally in 1990, what I call the last of the classic Archimedes, is the A540. This was the top-end machine. Could have up to 16 megabytes of memory, which is a fair bit even in 1990. It had a 30 megahertz ARM3. The ARM3 was the evolution of ARM2, but with a cache and a lot faster. So this talk will be centered around how these machines work, not the more modern machines. So around 1987, what else was available? This is a random selection of machines. Apologies if your favorite machine is not on this list. It wouldn't fit on the slide otherwise. So at the start of the 80s, we had the exotic things like the Apple Lisa and the Apple Mac, very expensive machines. The Amiga, I had to put in here, started off relatively expensive. Of course, the Amiga 500 was very good value for money, very capable machine. But I'm comparing this more to PCs and Macs, because that was the sort of market it was going for. And although it was an expensive machine, compared to Macintosh, it was pretty cheap. I even put a Next Cube on there. I figured that I'd heard that they were incredibly expensive, and actually compared to Macintosh, they're not that expensive at all. Oh well, I don't know which one I would have preferred. But. So the first question I asked them, the first thing they told me, so why was it built? I used them in school, and as I said, had one at home, but I was never really quite sure what it was for, and I think a lot of the Acorn marketing wasn't quite sure what it was for either. They told me it was the successor to the BBC Micro, this 8-bit machine, lovely 6502 machine, incredibly popular, especially in the UK. And the goal was to make a machine that was 10 times the performance of this. The successor would be 10 times faster at the same price. And the thing I didn't know is they had been inspired, the team at Acorn had seen the Apple Lisa and the Xerox Star, which comes from the famous Xerox Alto at Xerox PARC, first GUI workstation in the 70s, monumental machine. They'd been inspired by these machines, and they wanted to make something very similar. So this is the same story as the Macintosh. They wanted to make something that was desktop machine for business, for office automation, desktop publishing, and that kind of thing. I'd never really understood this before, so this inspiration came from the Xerox machines. It was supposed to be obviously a lot more affordable and a lot faster. So this is what happens when Acorn marketing gets hold of this vision. So the Xerox Star on the left is this nice, sensible business machine. Someone's wearing a nice, crisp suit, banging their microphone. And it gets turned into the very Cambridge tweed version on the right. So apparently it's illegal to program one of these if you're not wearing a top hat, but no one told me that when I was a kid. And yeah, my court case comes up next week. So Cambridge is a bit of a funny place, and for those that have been there, this picture on the right sums it all up. So they began Project A, which was build this new machine. And they looked at the alternatives, They looked at the processors that were available at that time, the 286, the 68K, the NatSemi 32016, which was an early 32-bit machine, a bit of a weird processor. And they all had something in common, that they were ridiculously expensive and, in Tudor's words, a bit crap. They weren't a lot faster than the BBC Micro. They're a lot more expensive. They're much more complicated in terms of the processor itself, but also the system around them was very complicated. They need lots of weird support chips. This just drove the price up of the system, and it wasn't going to hit that 10 times performance, let alone at the same price point. They'd visited a couple of other companies designing their own custom silicon. They got this idea in about 1983. They were looking at some of the RISC papers coming out of Berkeley, and they were quite impressed by what a bunch of grad students were doing. They managed to get a working RISC processor. And they went to Western Design Center and looked at the 6502 successors being designed there. And they had a positive experience. They saw a bunch of high school kids with Apple IIs doing silicon layout, and they thought, okay, well, they'd never designed a CPU before at Acorn. Acorn hadn't done any custom silicon to this degree. But they were buoyed by this, and they thought, okay, well, maybe RISC is the secret that we can do this. And this was not really the done thing in this time frame, and not for a company the size of Acorn, but they designed their computer from scratch. They designed all of the major pieces of silicon in this machine. And it wasn't about designing the ARM chip. Hey, we've got a processor, cool, what should we do with it? But it was about designing the machine that ARM and the history of that company has kind of benefited from. But this was all about designing the machine as a whole. They're a tiny team. There were a handful of people, about a dozen-ish, that did the hardware design. A similar sort of order for software and operating systems on top, which is orders of magnitude different from the IBMs and Motorola's and so forth that were designing computers at this time. RISC was the key. It needed to be incredibly simple. One of the other experiences they had was they went to a CISC processor design center. They had a team of a couple of hundred people, and they were on revision H, and it still had bugs, and it was just this unwieldy, complex machine. So RISC was the secret. Steve Ferber has an interview somewhere that he jokes about Acorn management giving him two things. The special sauce was two things that no one else had. He had no people and no money. So it had to be incredibly simple. It had to be built on a shoestring, as Jamie said to me. So there were lots of corners cut, but in the right way. I would say corners cut, that sounds ungenerous. There were some very shrewd design decisions, always weighing up cost versus benefit. And I think they erred on the correct side for all of them. So Steve sent me this picture. He's got a cameo here. That's the outline of him in the reflection on the glass there. He's got this up in his office. So he led the hardware design of all of these chips at Acorn. Across the top, we've got the original ARM, the ARM1, the ARM2, and the ARM3. You can guess the naming scheme. And the video controller, memory controller, and I/O controller. You can sort of see their relative sizes, and it's kind of pretty. This was also on a process where you could really point at that and say, oh, that's the register file. And you can see the cache over there. It's, you can't really do that nowadays with modern processors. Okay, so a little bit about the specification, what it could do. The end product, so I mentioned they all had this ARM2 at 8 megahertz, up to 4 megs of RAM. 26-bit addresses, remember that, that's weird. So a lot of 32-bit machines had 32-bit addresses, or the ones that we know today do. That wasn't the case here, and I'll explain why in a minute. The A540 had its updated CPU. The memory controller had an MMU, which was unusual for machines of the mid-80s. So it could support, the hardware would support virtual memory, page faults, and so on. It had decent sound. It had 8-channel sound, hardware mixed and stereo. It was 8-bit, but it was logarithmic, so it was a bit like ULAW, if anyone knows that, instead of PCM. So you got more precision at the low end, and it sounded to me a little bit like 12-bit PCM sound, so it's quite good. Storage-wise, it's the same floppy controller as the Atari ST. It's fairly boring. Hard disk controller was a horrible standard called ST506 MFM drives, which were very, very crude compared to the disks we have today. Keyboard and mouse, nothing to write home about. I mean, it was a normal keyboard. It was nothing particularly special going on there. And printer port, serial port, and some expansion slots, which I'll outline later on. The thing that I really liked about the Arc was the graphics capabilities. It was fairly capable, especially for a machine of that era and of the price. It just had a flat frame buffer. So it didn't have sprites, which is unfortunate. It didn't have oblitter and bit planes and so forth. But the upshot of that is that it was dead simple to program. It had a 256 color mode, 8 bits per pixel. So it's a byte. And it's all just laid out as a linear string of bytes. So it was dead easy to just write some really nice optimized code to just split stuff to the screen. Part of the reason why there isn't oblitter is actually the CPU was so good at doing this. Color-wise, so it's got paletted modes out of a 4096 color palette. Same as the Amiga. Has this 256 color mode, which is different. The big high-end machines, the top-end machines, the A540 and the A400 series, could also do this very high-res, 1152 by 900, which was more of a workstation resolution. So if you bought a Sun workstation, a Sun 3 in those days could do this in some higher resolutions. But this was really not seen on computers that might have in the office or school or education at that end of the market. And it was quite clever the way they did that. I'll come back to that in a sec. But for me, the thing about the Arc, for the money, it was the fastest machine around. It was definitely faster than 386s and all the stuff that Motorola was doing at the time by quite a long way. It was almost 8 times faster than a 68K at about the same clock speed. And that's to do with its pipelining and to do with it having a 32-bit word and a couple of other tricks. Again, I'll show you later on what the secret to that performance was. It's about mini computer speed. And compared to some of the other RISC machines at the time, it wasn't the first RISC in the world. It was the first cheap RISC and the first RISC machine that people could feasibly buy and have on their desks at work or in education. And if you compare to something like the MIPS or the SPARC, it was not as fast as a MIPS or SPARC chip. It was also a lot smaller, a lot cheaper. Both of those other processors had very big die. They needed other support chips. They had huge packages, lots of pins, lots of cooling requirements. And so all this really added up. So I priced up a Sun 4 workstation at the time, and it was well over 4 times the price of one of these machines. And that was before you add on extras such as disks and network interfaces and things like that. So it was very good, very competitive for the money. And if you think about building a cluster, then you could get a lot more throughput. You could network them together. So this is about as far as I got when I was a youngster. I wasn't brave enough to really take the machine apart and poke around. Fortunately now it's 30 years old and I'm fine. I'm qualified in doing this. I'm going to take it apart. Here's the motherboard. It's quite a nice, clean design. This was built in Wales, for anyone that's been to the UK. Very unusual these days for anything to be built in the UK. It's got several main sections around these 4 chips. So remember the Steve photo earlier on. This is the chipset, the ARM, MEMC, BIDC, IOC. So the IO side of things happens over on the left, video and sound on the top right, and the memory and the processor in the middle. It's got megabyte on board, and you can plug in an expansion for 4 megabytes. So memory map from the software view. I mentioned this 26-bit addressing, and I think this is one of the key characteristics of one of these machines. So you have a 64 megabyte address space. And it's quite packed. There's quite a lot of stuff shoehorned into here. So there's the memory. The bottom half of the address space, 32 megabytes of that, is the processor's got user space and privilege modes. It's got a concept of privilege within the processor execution. So when you're in user mode, you only get to see the bottom half. And that's virtual mapped. There's the MMU, or map pages into that space. And then when you're in supervisor mode, you get to see the whole of the rest of the memory, including the physical memory and various registers up the top. The thing to notice here is there's stuff hidden behind the ROM. This address space is very packed together. So there's a requirement for control registers for the memory controller, for the video controller, and so on. And they're write-only registers in ROM, basically. So you write to the ROM, and you hit these registers. Kind of weird when you first see it, but it's quite a clever way to fit this stuff into the address space. So it all started with the ARM1. Sophie Wilson designed the instruction set late 1983. Steve took the instruction set and designed the top level, the block, the microarchitecture of this processor. So this is the data path and how all the control logic works. And then the VLSI team then implemented this, did their own custom cells. There's custom data path and custom logic throughout this. And it took them about a year all in. Well, 1984, they'd sort of, this Project A really kicked off early 1984. And this teched out first thing early 1985. The design process, the guys gave me a little bit of, Jamie Urquhart and John Biggs gave me a bit of an insight into how they worked on the VLSI side of things. So they had an Apollo workstation, just one Apollo workstation, a DN600. This was a 68K based washing machine, as Jamie described it. It was this huge thing. It cost about £50,000. It was incredibly expensive. And they designed all of this with just one of these workstations. Jamie got in at 5 a.m., worked until the afternoon, and then let someone else on the machine. So they shared the workstation. They worked shifts so that they could design this whole thing on one workstation. So this comes back to that it was designed on a bit of a shoestring budget. When they got a couple of other workstations later on in the project, there was an allegation that the software might not have been licensed initially on the other workstations. The CAD software might have been, I can neither confirm nor deny whether that's true. But, so Steve wrote a BBC Basics simulator for this when he's designing this block level microarchitecture. Ran on his BBC Micro. So this could then run real software. There could be a certain amount of software development, but then they could also validate that the design was correct. There's no cache on this. This is quite a large chip. 50 square millimeters was the economic limit of those days for this part of the market. There's no cache. That also would have been far too complicated. So this was also, I think, quite a big risk, no pun intended, that the aim of doing this with such a small team, that they were all very clever people, but they hadn't all got experience in building chips before. And I think they knew what they were up against. And so not having a cache or complicated things like that was the right choice to make. I'll show you later that that didn't actually affect things. So this was a RISC machine. If anyone has not programmed ARM in this room, then get out at once. But if you have programmed ARM, this is quite familiar with some differences. It's a classical 3-operand RISC. It's got free shift on one of the operands for most of the instructions, so you can do things like static multiplies quite easily. It's not purist RISC, though. It does have load, store, multiple instructions. So these will, as the name implies, load or store a multiple number of registers in one go, so one register per cycle, but it's all done through one instruction. This is very not RISC. Again, there's a good reason for doing that. So ARM1 comes back, and it gets plugged into a board that looks a bit like this. This is called the A2P, the ARM second processor. It plugs into a BBC Micro. Basically, there's a thing called the tube, which is sort of a FIFO-like arrangement. The BBC Micro can send messages one way, and this can send messages back. And the BBC Micro has the disks, it has the I/O, the keyboard, and so on. And that's used as the host to then download code into 1 megabyte of RAM up here, and then you can run the code on the ARM. So this was the initial system, 6 megahertz. The thing I found quite interesting about this, I mentioned that Steve had built this BBC Basic simulation. One of the early bits of software that could run on this, Sophie had ported BBC Basic to ARM and written an ARM version of this. So the basic interpreter was very fast and very lean, and it was running on this board early on. They then built a simulator called ASIM, which was an event-based simulator for doing logic design. And all of the other chips in the chipset were simulated using ASIM on ARM1, which is quite nice. So this was the fastest machine that they had around. They didn't have, the thousands of machines in the cluster like you'd have in a modern company doing EDA. They had a very small number of machines, and these were the fastest ones they had about. So ARM2 was simulated on ARM1 and all the other chipset. So then ARM2 comes along. So that's a year later. This is a shrink of the design. It's based on the same basic microarchitecture, but it has a multiplier now. It's a Booth multiplier, so it's a worst case 16 cycle multiply. It does 2 bits per clock. Again, no cache, but one thing they did add in ARM2 was banked registers. So some of the processor modes, I'll mention a bit, there's an interrupt mode. Next slide. Some of the processor modes will basically give you a different view on registers, which is very useful. These were all validated at 8 megahertz. So the product was designed for 8 megahertz. The company that built them said, okay, put the stamp on the outside saying 8 megahertz. There's 2 versions of this chip, and I think they're actually the same silicon. I've got a suspicion that they're the same. They just tested this batch and saying, that works at 10 or 12. So on my project list is overclocking my A3000 to see how fast it will go, see if I can get it at 12 megahertz. Okay, so the banking of the registers. ARM's got this, even modern 32-bit ARMs have got a type of interrupt, an IRQ, pronounced IRK in English, and FIQ, pronounced FIC in English. I appreciate it doesn't mean quite the same thing in German, so I'll call it FIQ from here on in. And FIQ mode has this property where the top half of the registers are effectively different registers when you get into this mode. So this lets you, first of all, you don't have to back up those registers when you're FIQ handler. And secondly, if you can write an FIQ handler using just those registers, and there's enough for doing most basic tasks, you don't have to save and restore anything when you get an interrupt. So this is designed specifically to be a very, very low overhead interrupt mode. So I'm coming to why there's a 26-bit address space, and so I found this link very, very unintuitive. So unlike 32-bit ARM, the more modern 1990s onwards ARMs, the program counter, register 15, doesn't just contain the program counter, but it also contains the status flags and the processor mode, and effectively all of the machine state is packed in there as well. So I asked the question, well, why 64 megabytes of address space? What's special about 64? And Mike told me, well, you're asking the wrong question, it's the other way around. What we wanted was this property that all of the machine state is in one register. So this means you just have to save one register. I was like, well, what's the harm in saving 2 registers? And he reminded me of this FIQ mode. Well, if you're already in a state where you've really optimized your interrupt handler so that you don't need any other registers to deal with, you're not saving and restoring anything apart from your PC, then saving another register is 50% overhead on that operation. So that was the prime motivator, was to keep all of the state in one word. And then once you take all of the flags away, you're left with 24 bits for a word-aligned program counter, which leads to 26-bit addressing. And that was then seen as, well, 64 megs is enough. There were machines in 1985 that could conceivably have more memory than that, but for a desktop that was still seen as a very large, very expensive amount of memory. The other thing, you don't need to reinvent another instruction to do a return from exception. So you can return using one of your existing instructions. In this case, it's a subtract into PC, which looks a bit strange, but trust me, that does the right thing. So the memory controller, this is, I mentioned the address translation, so this has an MMU in it. In fact, the thing directly on the left-hand side, I was worried that these slides actually might not be the right resolution and they might be sort of too small for people to see this. And the fact it's the size of a house is really useful here. So the left-hand side of this chip is the MMU. This chip's the same size as ARM2. Yeah, pretty much. So that's part of the reason why the MMU is on another chip. ARM2 was as big as they could make it to fit the price. As you, I don't know if anyone here has done silicon design, but as the area goes up, effectively your yield goes down, and the price, it's a non-linear effect on price. So the MMU had to be on a separate chip, and it's half the size of that as well. MMC does mundane things like it drives DRAM, it does refresh for DRAM, and it converts from linear addresses into row and column addresses, which DRAM takes. So the key thing about this ARM and MEMC binding is the key factor of performance is making use of memory bandwidth. When the team had looked at all the other processors in Project A before designing their own, one of the things they looked at was how well they utilized DRAM. 68K and the NatSemi chips made very, very poor use of DRAM bandwidth. Steve said, well, okay, the DRAM is the most expensive component of any of these machines, and they're making poor use of it. And I think a key insight here is if you maximize that use of the DRAM, then you're going to be able to get much higher performance than those machines. And so it's 32 bits wide. The ARM is pipelined, so it can do a 32-bit word every cycle. And it also indicates whether it's sequential or non-sequential addressing. This then lets your MEMC decide whether to do an N cycle or an S cycle. So there's a fast one and a slow one, basically. So when you access a new random address in DRAM, you have to open that row, and that takes twice the time. It's a 4 megahertz cycle. But then once you've accessed that address, and then once you're accessing linearly ahead of that address, you can do fast page mode accesses, which are 8 megahertz cycles. So ultimately, that's the reason why these load store multiples exist, the non-RISC instructions. They're there so that you can stream out registers to the back end and make use of this DRAM bandwidth. So a store multiple, this is just a simple calculation. For 14 registers, you're hitting about 25 megabytes a second out of 30. So this is, it's not 100%, but it's way more than a tenth or an eighth, which a lot of the other processors were using. So this was really good. This is the prime factor of why this machine was so fast, is effectively the load store multiple instructions and being able to access this stuff linearly. So the MMU is weird. It's not a TLB in the traditional sense. So TLBs today, if you take a MIPS chip or something where the TLB is visible to software, it will map a virtual address into a chosen physical address, and you'll have some number of entries, and you more or less arbitrarily, poke an entry in with a certain mapping in it. The MEMC does it upside down, so it says it's got a fixed number of entries for every page in DRAM, and then for each of those entries, it checks an incoming address to see whether it matches. So it has all of those entries that we showed on the chip diagram a couple of slides ago, that big left-hand side had that big array. All of those effectively are just storing a virtual address and then matching it. They have a comparator. And then one of them lights up and says, yes, it's mine. So effectively, a physical page says that virtual address is mine instead of the other way around. So this also limits your memory. If you're saying I have to have one of these entries on chip per page of physical memory, and you don't want pages to be enormous, the 32K, if you do the maths, there's 4 megabytes over 128 pages. It's a 32K page. If you don't want the page to get much bigger than that, and trust me, you don't, then you need to add more of these entries, and it's already half the size of the chip. So effectively, this is one of the limits of why you can only have 4 megabytes on one of these memory controller chips. Okay, so VIDC is the core of the video and sound system. It's a set of FIFOs and a set of on-chip digital analog converters for doing video and sound. You stream stuff into the FIFOs, and it does the display timing and palette lookup and so forth. It has an 8-bit mode I mentioned, which is slightly strange. It also has an output for a transparency bit. So in your palette, you can set 12 bits of color, but you can set a bit of transparency as well. So you can do video gen locking quite easily with this. So there was a revision later on. Tudor explains that the very first one had a bit of crosstalk between the video and the sound. So you'd get sound with noise on it that was basically video noise. And it's quite hard to get rid of. And so they did this revision, and the way he fixed it was quite cool. They shuffled the power supply around and did all the sensible engineering things. But he also filtered out a bit of the noise that was being output on as the sound. He inverted it and then fed that back in as the reference current for the DACs. So they were sort of self-compensating and took the noise, a bit like the noise-cancelling headphones. It was kind of a nice hack. And that was VidC 1A. Okay, the final one. I'm going to stop showing you chip plots after this, unfortunately, but just get your fill while we're here. And again, I'm really glad this is enormous for the people in the room and maybe those zooming in online. There's a cool little Illuminati eye logo in the bottom left corner. So I feared that you weren't going to be able to see, and I didn't have time to do a zoomed in version. But okay, so IOC is the center of the I/O system. As much of the I/O system as possible, all the random bits of glue logic to do things like timing, some peripherals are slower than others, lives in IOC. It contains a UART for the keyboard. So the keyboard is looked after by an 8051 microcontroller, which is nice and easy. You don't have to do scanning in software. So this microcontroller just sends stuff up a serial port to this chip. So KART, keyboard, asynchronous receiver and transmitter. It was at one point called the fast asynchronous receiver and transmitter. Mike got forced to change the name. Not everyone has a 12-year-old sense of humor, but I admire his spirit. So the other thing it does is interrupts, all the interrupts go into IOC, and it's got masks and consolidates them effectively before sending an interrupt up to the ARM. The ARM can then check the status and do a fast response to it. So the Eye of Providence there, the little logo I pointed out, Mike said he put that in for future archaeologists to wonder about. Okay. That was it. I was hoping there'd be this big backstory about, he was in the Illuminati or something. Maybe he is, you're not allowed to say. Anyway. So just like the other dev board I showed you, so this one's A500 2P. It's still a second processor that plugs into a BBC Micro. It's still got this host having disk drives and so forth attached to it and pushing stuff down the tube into the memory here. But now finally all of the chipset are now assembled in one place. So this is starting to look like an Archimedes. It's got video out, it's got keyboard interface, it's got some expansion stuff. So this is bringing up an early software head start. But very shortly afterwards we got the A500 internal to Acorn. And this is really the first Archimedes. This is the prototype Archimedes. It's got a gorgeous grey brick sort of look to it, kind of concrete. It weighs like concrete too, but it has all the hallmarks. It's got the I/O interfaces. It's got the expansion slots that you can see at the back. It's got it runs the same operating system. Now, this was used for the OS development. There's only a couple of hundred of these made. Well, this is serial 222, so this was one of the last, I think. But yeah, only internal to Acorn. There were lots of nice tweaks to this machine. So the hardware team had designed this, Tudor designed this, as well as the video system. And he said, well, his A500 was the special one, that he had a video controller that he'd hand-picked one of the VidCs, so that instead of running at 24 megahertz, it would run at 56. So some silicon, there's variations in manufacture. So he found a 56 megahertz part, and so he could do, I think it was 1024 by 768, which was way out of spec for the rest of the Archimedes. So he had the really cool machine. They also ran some of them at 12 megahertz as well, instead of 8. So this is a massive performance improvement. I think it used expensive memory, which was kind of out of reach for the product. Right. So believe me, this is the simplified circuit diagram. The technical reference manuals are available online if anyone wants the complicated one. But the main parts are displayed. We've got the ARM, MEMC, VidC, and some RAM. And we'll have a little walk through them. So the clocks are generated actually by the memory controller. Memory controller gives the clocks to the ARM. And the main reason for this is that the memory controller has to do some slow things now and then. It has to open pages of DRAM. There's refresh cycles and things. So it stops the CPU. It generates the clock, and it pauses the CPU by stopping that clock from time to time. When you do a DRAM access, the address bus along the top, the ARM outputs an address that goes into the MEMC. And the MEMC then converts that. It does an address translation, and then it converts that into a row and column address suitable for DRAM. And then if you're doing a read, DRAM outputs the address, outputs the data onto the data bus, which ARM then sees. So it's kind of, MEMC is the critical path on this, but the address flows through MEMC effectively. Notice that MEMC is not on the data bus. It just gets addresses flowing through it. This will become important later on. ROM is another slow thing, another reason why MEMC might slow down the access from the CPU. Works similar sort of way. There's also a permission check done when you're doing the address translation, user permission versus OS supervisor. And so this information is output as part of the cycle when the ARM does that access. If you miss in that translation, you get a page fault or a permission fault, then an abort signal comes back and you take an exception. And the ARM deals with that in software. The data bus is a critical path, and so the I/O stuff is buffered, it's kept away from that. So the I/O bus is 16 bits. There are not a lot of 32-bit peripherals around in those days. All the peripherals are 8 or 16 bits, so that's the right thing to do. The IOC decodes that, and there's a handshake with memc. If it needs more time, if it's accessing one of the expansion cards and the expansion card has got something slow on it, then that's dealt with the IOC. So I mentioned the interrupt status. That all gets funneled into IOC and then back out again. There's a vsync interrupt, but not an hsync interrupt. You have to use timers for that, really annoyingly. There's one timer, there's a 2 megahertz timer available. I think I had that on a previous slide, I forgot to mention it. So if you want to do funny palette switching stuff or copper bars or something, that's possible with the timers. It's also a simple hardware mod to make a real hsync interrupt as well. There's some spare interrupt inputs on the IOC as an exercise to the reader. So the bit that I really like about this system, I mentioned that the memc is not on the data bus. The VIDC is only on the data bus. It doesn't have an address bus either. And the VIDC is the thing responsible for turning the frame buffer into video, reading that frame buffer out of RAM, and so on. So how does it actually do that RAM read without the address? Well, the memc contains all of the registers for doing this DMA. The start of the frame buffer, the current position and the size and so on. They will live in the memc. So there's a handshake where the VIDC sends a request up to the memc when its FIFO gets low. The memc then actually generates the address into the DRAM. DRAM outputs that data, and then gives the memc gives an acknowledge to the excuse me, too many chips. The memc gives an acknowledge to the VIDC, which then latches that data into the FIFO. So this partitioning is quite neat. A lot of the video DMA stuff, well, the video DMA stuff all lives in memc, and there's this kind of split across the two chips. The sound one, I've just highlighted one interrupt that comes from memc. Sound works exactly the same way, except there's a double buffering scheme that goes on, and when one half of it becomes empty, you get an interrupt. So you can refill that, so you don't glitch your sound. So this all works really very smoothly. So finally, the high-res mono thing that I mentioned before, it was quite a novel way they did that. Tudor had realized that with one external component, a shift register running very fast, he could implement this very high-resolution mode without really affecting the rest of the chip. So the VIDC still runs at 24 megahertz, which is sort of VGA resolution. It outputs on a digital bus, it was a test port originally. It outputs 4 bits, so 4 pixels in one chunk at 24 megahertz. And then this external component then shifts through that at 4 times the speed. So there's one component. I mean, this is a very cheap way of doing this, and as I said, this high-res mode is very unusual for machines of this era. I've got a feeling an A500, the top-end machine, if anyone's got one of these and wants to try this trick, then please get in touch. I've got a feeling an A500 will do 1280 by 1024 by overclocking this. I think all of the parts survive it, but for some reason Acorn didn't support that on the board. And finally, clock selection. The VIDC on some of the machines, quite flexible set of clocks for different resolutions, basically. So memc is not on the data bus. How do we program it? It's got registers for DMA, and it's got all this address translation. So the memory map I showed before has an 8 megabyte space reserved for the address translation registers. It doesn't have 8 megabytes of, it doesn't have 2 million 32-bit registers behind there, which is a hint of what's going on here. So what you do is you write any value to this space, and you encode the information that you want to put into one of these registers in the address. So for this address, top 3 bits are 1. It's in the top 8 megabytes of the 64 megabyte address space. And you format your logical physical page information in this address, and then you write any byte, effectively. This sort of feels really dirty, but also really a very nice way of doing it, because there's no other space in the address map. And this reads to the price balance. So it's not worth having an address bus going into memc, costing 32 more pins just to write these registers, as opposed to playing this sort of trick. If you have that address bus just for that, data bus just for that, then you have to go up to a more expensive package. And this was really in their minds. A 68-pin chip versus an 84-pin chip, it was a big deal, right? So everything, they really strived to make sure it was in the very smallest package possible. And this system partitioning effort led to these sorts of tricks to then program it. So on the A540, we get multiple MEMCs. Each one is assigned a colored stripe here of the physical address space. So you have a 16 megabyte space. Each one looks after 4 megabytes of it. But then when you do a virtual access, in the bottom half, you use a space regular program access. All of them light up, and all of them will translate that address in parallel. And one of them hopefully will translate and then energize the RAM to do the read, for example. When you put an ARM3 in this system, the ARM3 has its cache, and then the address leads into the MEMC. So then that means that the address is being translated outside the cache, or after the cache. So you're caching virtual addresses, and as we all know, this is kind of bad for performance, because whenever you change that virtual address space, you have to invalidate your cache. Or tag it, but they didn't do that. There's other ways of solving this problem, but basically on this machine, what you need to do is invalidate the whole cache. It's quite a quick operation, but it's still not good for performance to have an empty cache. The only DMA present in the system is for the video and sound. I/O doesn't have any DMA at all. And this was another area where, as a younger engineer, I was, this is crap, why didn't they have DMA? That would be way better. DMA is the solution to everyone's problems, as we all know. And I think the quote on the right ties in with the Acorn team's discovery that all of these other processors needed quite complex chipsets, quite expensive support chips. So the quote on the right says that if you've got, so some chipset vendors will be charging more for their DMA devices even than the CPU. So not having a dedicated DMA engine on board was a massive cost saving. The comment I made on the previous two slide about the system partitioning, putting a lot of attention into how many pins were on one chip versus another, how many buses were going around the place. Not having IOC having to access memory was a massive saving in cost for the number of pins and the system as a whole. The other thing is the FIQ mode was effectively the means for doing I/O. The FIQ mode was designed to be an incredibly low overhead way of doing programmed I/O, having the CPU do the I/O. So it was saying that the CPU is going to be doing all of the I/O stuff, but let's just optimize it. Let's make it as good as it could be, and that's what led to the programmed I/O. Also remember, ARM2 didn't have a cache. And if you don't have a cache on your CPU, then DMA is going to hold up the CPU anyway. So on those cycles, DMA is not any performance gain. You may as well get the CPU to do it, and then get the CPU to do it in the lowest overhead way as possible. I think this it can be summarized as bringing the risk principles to the system. So the risk principles say for your CPU, don't put anything in the CPU that you can do in software. And this is saying, okay, well actually software can do the I/O just as well without a cache as a DMA system, so let's get software to do that. And I think this is a kind of a nice way of seeing it. This is part of their cost optimization for really very little degradation in performance compared to doing it in hardware. So this is an I/O card, Euro cards, they're nice and easy. The only thing I wanted to say here was this is my SCSI card, and it has a ROM on the left-hand side. And so it was common. This is an expansion ROM, basically, many, many years before PCI made this popular. Your drivers are on this ROM. This is a SCSI disk plugging into this, and you can plug this card in and then boot off the disk. You don't need any other software to make it work. So this is just a very nice user experience. There was no messing around with configuring I/O windows or interrupts or any of the ISA sort of stuff that was going on at the time. So to summarize some of the hardware stuff that we've seen, the ARM is pipelined, and it has the load store multiple instructions, which make for very high bandwidth utilization. That's what gives it its high performance. The machine was really simple, so the attention to detail about separating, partitioning the work between the chips and reducing the chip cost as much as possible. Keeping that balanced was really a good idea. The machine was designed when memory and CPUs were about the same speed. So this is before that kind of flipped over. An 8 megahertz ARM2 was designed to use 8 megahertz memory. And there's no need to have a cache at all on there. These days, it sounds really crazy not to have a cache on a CPU, but if your memory is not that much slower, then this is, a huge cost saving. But it was also risk saving. This was the first real proper CPU, if we don't count ARM1. Let's say ARM1 was a test, but ARM2 was the first product CPU. And having a cache on that would have been a huge risk for a design team that hadn't dealt with structures that complicated at that point. So that was the right thing to do, I think. And I'm talking about DMA. I'm actually a converse on this. I thought this was crap, and actually I think this was a really good example of balanced design. What's the right tool for the job? Software's going to do the I/O, so let's make sure that FIQ mode, it makes sure that's as low overhead as possible. We talked about system partitioning. The MMU, I'm in two minds about. I still think it's weird and backward. I think there is a strong argument, though, that a more familiar TLB is massively complicated compared to what they did here. And I think the main drive here was not just area on the chip, but also to make it much simpler to implement. So it worked, and I think they really didn't have that many shots at doing this. This wasn't a company or a team that could afford to have many goes at this product. And I think that says it all. So I think they did a great job. Okay, so the OS story is a little bit more complicated. Remember, it's going to be this office automation machine, a bit like a Xerox Star. It was going to have this wonderful, high-res mono mode, and people are going to be laser printing from it. So just like Xerox PARC, Acorn started a Palo Alto-based research center and had Californians in beanbags writing an operating system using a microkernel in Modular 2. All of the trendy boxes ticked here for the mid-80s. It was, by the sounds of it, a very advanced operating system, and it did virtual memory and so on. It was very resource hungry, though, and it was never really very performant. Ultimately, the hardware got done quicker than the software, and after a year or two, management got the jitters. Hardware was looming and said, well, next year we're going to have the computer ready, where's the operating system? And the project got canned. And this is a real shame. I'd love to know more about this operating system. Virtually nothing is documented outside of Acorn. Even the people I spoke to didn't work on this. A bunch of people in California that kind of disappeared with it. So if anyone has this software archived anywhere, then get in touch. The Computer Museum around the corner from me is raring to go on that. That would be a really cool thing to archive. So anyway, they had now a desperate situation. They had to go to Plan B, which was in under a year write an operating system for the machine that was on its way to being delivered. And it kind of shows. Arthur was, I think the team did a really good job in getting something out the door in half a year, but it was a little bit flaky. RISC-OS then a year later developed from Arthur. I don't know if anyone's heard of RISC-OS, but this is, Arthur is very niche, and basically got completely replaced by RISC-OS because it was a bit less usable than RISC-OS. Another really strong point that this had is it's quite a big ROM, so 2 megabytes going up, half a megabyte in the 80s going up to 2 megabytes in the early 90s. There's a lot of stuff in ROM. One of those things was BBC Basic 5. I know it's 2019, and I know Basic is basic, but BBC Basic is actually quite good. It has procedures, and it's got support for all the graphics and sound. You could write GUI applications in Basic, and a lot of people did. It's also very fast. So Sophie Wilson wrote this with a very, very optimized Basic interpreter. I talked about the modules from Podules. This was the expansion ROM thing, so really great user experience there. But speaking of user experience, this was Arthur. I never used Arthur. I just dug out a ROM and had to play with it. It is bloody horrible. So that went away quickly. At the time also, so part of this emergency plan B was to take the Acorn Soft team, who were supposed to be writing applications for this, and get them to quickly knock out an operating system. So at launch, basically this was one of the only things that you could do with the machine. It had a great demo called Lander of a great game called Zarch, which is 3D space you could fly around. It didn't have serious business applications, and it was very, there was not much you could do with this really expensive machine at launch, and that really hurt it, I think. So then we get RISC-OS 2 in 1988, and this is now looking less like a sort of vomity sort of thing, much nicer machine. And then eventually RISC-OS 3. There's drag and drop between applications, there's all multitasking, there's outline fonts, anti-aliasing, and so on. So just lastly, I want to quickly touch on the really interesting operating system. So Acorn had a Unix operating system. So as well as being a CPU geek, I'm also a Unix geek, and I've always been fascinated by RISC geeks. These machines were astonishingly expensive. They were the existing Archimedes machines with a different sticker on. So that's an A540 with a sticker on the front. And this operating system was developed after, the Archimedes was already designed at that point when this operating system was being developed. So there's a lot of stuff about the hardware that wasn't quite right for a Unix operating system. 32K page size on a 4 megabyte machine really, really killed you in terms of your page cache and that kind of thing. They turned this into a bit of an opportunity, or at least they made good on some of this. There was quite a novel online decompression scheme for you could demand page in text from a binary, and it would decompress into your 32K page, but it was stored in a sparse way on disk. So actually the on-disk use was a lot less than you'd expect. The only way it would fit on some of the smaller machines. Also, Acorn Tech Author department designed the Cybertruck, it turns out. This was their view of the A680, which was an unreleased workstation. I love this picture. I like it's a piece of cheese or cake as the mouse. Is my favorite part. But this is the real machine. So this is an unreleased prototype I found at the Computing Museum. It's notable in that it's got 2 memsies, it's got 8 megs of RAM. It was only designed to run RISC-X, the Unix operating system. And it has high-res mono only, it doesn't have color. It was designed to run FrameMaker and drive laser printers and be a kind of desktop publishing workstation. I've always been fascinated by RISC-X, as I said. A while ago, I hacked around on ArcM for a while and got it booting in ArcM. I'd never seen this before, I've never used a RISC-X machine. So there we go, it boots, it's multi-user. But wait, there's more. It has a really cool little X server, a very fast one. I think Sophie Wilson again worked on the X server here, so it's very, very well optimized and very fast for a machine of its era. And it makes quite a nice little Unix workstation. It's quite a cool little system. By the way, Tudor, the guy that designed the VidC and the I/O system, called me a Sado for getting this working in there, so that's my claim to fame. Finally, and I want to leave some time for questions. There's a lot of useful stuff in ROM. One of them is BBC Basic. Basic has an assembler, so you can walk up to this machine with a floppy disk and write assembler. It has a special bit of syntax there. And then you can just call it. And so this is really powerful. So, at school or something with a floppy disk, you can do something that's a bit more than basic programming. And bizarrely, I managed to write that with only 2 or 3 tiny syntax errors after about 20 years away from this. So it's in there somewhere. Legacy-wise, the machine didn't sell very many, under 100,000 easily. I don't think it really made a massive impact. PCs had already taken off by then. The ARM processor, I'm not going to go on about the company. That's clear that obviously has changed the world in many ways. The thing that I really took away from this exercise was that a handful of smart people, not that many, order of a dozen, designed multiple chips, designed a custom computer from scratch, got it working, and it was quite good. And I think that this really turned people's heads. It made people think differently. That people that were not Motorola and IBM and really, really big companies with enormous resources could do this and could make it work. I think actually that led to the thinking that people could design their systems on chip in the 90s and that market taking off. So I think this was really key in getting people thinking that way. It was possible to design your own silicon. Finally, I just want to thank the people I spoke to and Adrian and Jason at the Centre for Computing History in Cambridge. If you're in Cambridge, then please visit there. It's a really cool museum. And with that, I'll wrap up. If there's any time for questions, then I'm getting a blank look. No time for questions?
There's about 5 minutes left for questions.
Fantastic. Okay, cool. Or come up to me afterwards. I'm happy to chat more about this. Thank you. Thank you.
The first question is for the internet.
Internet.
Signal Angel, that will be you. Oh, well, grab your microphones and I'll get first to the audio, to the room here. Send a microphone, please. Ask a question.
You mentioned that the system is making good use of the memory, but how is it actually not completely being stalled on memory if having no cache and same cycle time for the cache for the memory as for the CPU?
Good question. So how is it not always stalled on memory? Well, it is sometimes stalled on memory. When you do something that's non-sequential, you have to take one of the slow cycles. This was the end cycle.
Yep.
The key is you try and maximize the amount of time that you're doing sequential stuff. So on the ARM2, you wanted to unroll loops as much as possible, so you're fetching your instructions sequentially, right? You wanted to make as much use as load store multiples. You could load single registers with an individual register load, but it was much more efficient to pay that cost just once at the start of the instruction and then stream stuff sequentially. So you're right, it is still stalled sometimes, but that was still a good trade-off, I think, for a system that didn't have a cache for other reasons.
Thanks.
No worries.
Next question is for the internet.
Are there any Archons on sale right now? Or if you want to get into this kind of hardware, where do you get it?
Can you repeat the first sentence, please? Sorry, the first part.
If you want to get into this kind of hardware, if you want to buy it right now, where to?
Yeah, good question. So how do you get hold of one? Drive prices up on eBay, I guess, I hate to say. It might be fun to play around in emulators. I always prefer to sort of hack around on the real thing. Emulators always feel a bit strange. There are a bunch of really good emulators out there that are quite complete. Yeah, I think I would just go on auction sites and try and find one, unfortunately. They're not completely rare. I mean, that's the thing. They did sell, I'm not quite sure exact figure, but there were tens and tens of thousands of these things made. So I would look also in Britain more than elsewhere, although I understand that Germany had quite a few. If you can get your hold of one, though, I do suggest doing so. I think they're really fun to play with.
Okay, next question.
So I found myself looking at the documentation for the LDM SDM instructions while debugging something on ARM just last week.
Oh, great.
And just made me wonder, watching your talk, are there any quirks of the Archimedes that have crept into the modern ARM design and instruction set that you're aware of?
Most of them got purged. So the 26-bit addressing, there was a couple of strange uses of, there's an XOR instruction into PC for changing flags. So there was a great purge when the ARM6 was designed. And the ARM6 is, I should know, there's ARMv3. That's got 32-bit addressing, and lots of these weirdnesses got moved out. I can't think of, aside from just the resulting ARM32 instruction set being quite quirky and having a lot of the good quirks, the shifted register is a sort of a free thing you can do. For example, you can add one register to a shifted register in one cycle. I think that's a good quirk. So in terms of the inheriting that instruction set and not changing those things, maybe that counts.
Any further questions? Internet, any new questions? Nope. Okay. Well, in that case, a warm round of applause for
Thank you.
Mount Ovens.